Okay, so we are in Math 331. This is lecture, I think, 28. And so what we're going to do is we're going to continue doing our problem solvings. So we've been looking at various, games, riddles, challenges. So what we did last time was we did the tic-tac-toe game with bidding, right? This is one of the two ways that are standard to make tic-tac-toe an interesting game. The other one, which I've talked about briefly, is gobble tic-tac-toe. We have like the little Russian dolls, and you have the large, too medium, too small. There's lots of tweaks you can do. One of the tweaks you can do is you can gobble up a piece, and then later you can actually remove your piece, and the piece you gobbled is now restored to its position on the board. So it could be strategically useful to gobble up one of your pieces to protect that square, and then when you move over, now you've got a piece there as well. So the strategy becomes very interesting depending on what kind of twists you want to do, and the question is, how would you analyze stuff like that? So part of what I want to do is I want to keep the work you guys have to do at home to a minimal, but have good class participation about riddles. So I'm going to give you the bridge over troubled students. All right, so at least one person is laughing. What song is this a takeoff on? Bridge over troubled waters. If you can tell me why they play You Can Call Me Al at college football games across the country, I will give you extra credit. I would love to know how that started. I probably should just check Wikipedia, but I have been lazy. All right, so this is in honor of Simon and Garfunkel's Bridge Over Troubled Water. You have 4 students named 1, 2, 5, and 10. And amazingly, when they were born, their parents knew exactly what their walking speeds would be when they got older. It's amazing. And they named them exactly how long it would take them to cross the most important bridge in the country. They want to cross this bridge at night, so you need a flashlight or you can't see. There's no railing or anything like that. Okay? 2 people can go across the bridge at any moment in time. More than 2 people, and it collapses. So only 2 cross at once, need the flashlight. What do you think the objective is? To cross everyone over in a certain amount of time. So is it difficult to cross everyone over? No, crossing everyone over is trivial. Somebody give me a strategy that gets everybody across the bridge.
One goes with everyone.
Yeah, 1 walks over with 2 and comes back. 1 walks over with 5 and comes back. 1 walks over with 10 and comes back. I need to get my steps. So that's one way to do it. All right, how long would it be the 1 walks all method? How long would that be? So the first one, 1 walks 2 over and back. How long is that? 3. So I didn't say this. You travel at the slowest speed. So for 1 to walk 2 over and back would be 3. For 1 to walk 5 over and back would be 6. And to walk 10 over and back, so that's 20? Oh, it doesn't need to come back. Good. So it's 19. Right? So here's my first question. You haven't done any analysis on this yet. Do you think this is a good method or a bad method? What do you think? Oh, we did this one? Oh, this was a homework problem? Oh, we did this one. Okay. All right, so then you know that the answer is 17. Did we go through the formal way of finding 17? Okay, all right. So we know that this is not horrible. All right, we did do this as homework. Best is 17. So I think it's actually a little bit surprising that the best is 17, and the naive strategy of 1 goes with everybody is pretty good. So what I want to talk about is how you would really analyze a problem like this. Okay? So some of this is, I think, very similar to solving the quadratic formula or trying to find roots of a quadratic polynomial. A lot of times you can just look at things and you can see the solution. Other times you need a formal process because the one thing that works may be a little bit hard to see. Did we do the legal 21? Okay, good. So at least the second thing I prepared today is completely new. All right. So it's not bad that we've seen this before. When you look at this, what were some of your thoughts about how you would attack this?
first thought was that you know that you have to use 10 minutes to get the...
Good. At least 10 minutes. And actually, since the flashlight has to come back, it's got to be more than 10 minutes.
Yeah, well, yeah, just like you're going to have to spend 10 minutes on one trip.
You're going to have to spend 10 minutes on at least one trip, yes. So an interesting question would be, what would be the minimum? And I'm not saying that this could happen, but the minimum is at least... I'm sorry? I think it's a little bit larger than 11. I think you can prove the minimum is larger than 11. What would you think would be a minimum? So we would send 5 and 10 over, that would be 10 minutes. And then we would have to send 1 and 2 over, which would be 12 minutes. But we've got to get the flashlight back for 1 and 2 to go across. So the minimum is at least 13. Right? Oh, exactly. This is the phrase, at least. I agree that it should be more than 13. I'm just saying, we had a naive approximation that the minimum is at least 10. I'm refining it to the minimum is at least 13. We know the maximum is at most 19. So the question is just, how close are we? And again, we only have 4 players. Maybe we want to have more players than just 1, 2, 5, and 10. And maybe we want to have more general configurations than just 1, 2, 5, 10. A1, A2, ... AM. And how would you attack a general problem like that? How would you get some idea? Well, one possibility is you could keep doing maybe worst possible pairs. The worst possible pairs go over together. And then you have the fast person who's going to have to just keep making the trips back and forth, back and forth, back and forth. So that could basically be somewhat using the one strategy, but with a little bit of a twist. The one doesn't bring everybody over. Bad people go over together. And then somehow one has to be there. Oh, but wait a minute. If one is there, and then one comes back with a flashlight, and bad people go over, then one's on the wrong side. Right? So it seems reasonable that we would want to send bad people over together, and then have the fast person return with the flashlight. But if the fast person returns with the flashlight, then when the bad people go over, the flashlight's on the wrong side. So what would we do? We take the 2 fastest people, and the 2 fastest people go over together. And then they go over together, and then one of them, it doesn't matter which one, stays on that side, and then the other one, hope I can stop swinging backwards, returns with the flashlight. Then they send the 2 bad people over. Then the fast person who stayed on the other side can come back. And now once they come back, they give the flashlight, and now the next 2 bad people... No, then I guess then the 2 fast people would go over again, leave somebody there, and come back. And then you could send 2 bad people over again, and then the flashlight can come back. And so you would almost have to just keep having a trip where you bring slow people over together after it's been prepared for them by having a fast person waiting. So this suggests the following. We start off with 1 and 2 travel over with the flashlight. Then it doesn't matter who comes back 1 or 2, because one of them comes back now, the other one comes back the next time. So then we'll send 1 back. Then we can send 5 and 10 over. I guess I'm doing it this way. And now we can send 2 back. And then we can send 1 and 2 over. And so the cost of this would be 2, 1, 10, 2, 2, which is 17. So this is my thought process of how to get here. To see that I want to send, I want to get 1 and 2 together to transfer the flashlight and leave the flashlight there. I don't want to have somebody walking with 5, somebody walking with 10. Because that's going to take at least 15 minutes just for those, plus the trips back and forth. So what clues make this easy? Well, on the homework I told you the target time was 17 minutes. If I don't tell you the target time is 17 minutes and I ask you what's the best you can do you still come up with the 17 or do you come up with a different value?
Always happy at 19.
You might be happy at 19 and say, this is not bad. In the real world, you frequently do not know what the answer is. Unless it's something like the Riemann hypothesis, which we know is true, we just don't know how to prove it. So sometimes you do know what's right, but you don't know how to show it rigorously. Other times you can do some estimates and get some range. So by doing a little bit of analysis here, this gives us a sense of how to view the problem. But is this a proof that this is best? No. This just shows that this is better than 19. Could there be something better than 17? So this is a small enough problem that we could do it exhaustively. How could we attack this problem? What kind of techniques could we use to formally assault this? I think just doing a little bit of analysis and saying we want 5 and 10 to go together, it then suggests that we want 1 and 2 to go together and just be the transferring flashlight team. And this suggests how you might want to try to generalize things if you have a bunch of people. But maybe it matters how the speeds are relative to the speeds of the 2 fastest. And that the answer could depend. Anybody sees Utopia? So if you have the sloths who need to cross, they are going to be so slow. You want the 2 sloths together. And what is it, Officer Judy Hopps? Yeah, she could probably go very, very fast, right? Okay. Now, anybody have any ideas about how we could formally investigate all possibilities? Yes.
We can perhaps say that for each person,
Right.
in order for all of them to get to the other end,
Mm-hmm.
each of them must travel odd times across.
Okay, everybody must travel an odd number of times.
And then we can just, I guess we can just check. No.
Okay, so we have a nice number that everybody must travel an odd number of times. And if we don't travel an odd number of times, it's clearly not going to work. Okay? But that's still a lot of things to check. But it is at least nice to know that we must have an odd number of travels. So, must have each person travel an odd number of times and cannot exceed 19 minutes. Because we know we can do it in 19 minutes. If you want, we might even know we can do it in 17 minutes. Depending on have we been clever. Anybody take a lot of physics classes here? Okay. So this may be just a personalized lecture right now, but anybody remember gravity? What kind of force is gravity? Anybody remember anything about the gravitational force? Inverse square. So it's a central force, and it's proportional to 1 over the square of the distance between them. So physicists often use alpha for proportional. I'll try proportional. What about electricity? Same. And this is one of the great things in physics, is if you have the same laws governing different phenomena, you can immediately write down the solutions if you know the solutions in one. Now, there are often different features. In electricity, we can have positive and negative charges. We have not found positive and negative masses. In electricity, opposite charges attract, like charges repel. Here, everything is the same and it always attracts. The size of the effect is very different. The number of orders of magnitude between the forces is huge. But a lot of the mathematics is very similar. And you can transfer what you know in gravity to what you know in electricity and magnetism. The goal is, can we transfer this problem to something we've seen before? Now, a lot of problems have a beautiful feature that they may be hard to solve but easy to verify. It's not that hard to verify that we can do this in 17 minutes. I just have to exhibit a path that does it in 17 minutes. How do we find something that will do it optimally? Well, let's look at the possibilities. So if we have blah, blah, star, or star, blah. I claim that no matter where we are, we're in one of those two states. What do you think this will mean? What do you think star might be? The flashlight. And what do you think the two different sides are?
Just whoever.
Yeah, whoever's on the left side of the bridge, whoever's on the right side of the bridge, and where's the flashlight? I can write down every configuration in this form. We start off at 1, 2, 5, 10, flashlight, nothing. Where could we move? We can send 2 people over with the flashlight. Could we send 1 person over with the flashlight? That would be useless. Is there ever a situation in this game where we would send 1 person over with the flashlight?
The last.
So do we have to wait on the last turn that maybe 1 person travels with the flashlight? So let's think. Is it possible that on the last step, a person has to walk with a flashlight? Right, we're not going to chuck. There is no chucking of flashlights, right? For the last person to be traveling with a flashlight, they had to get the flashlight. How could they get the flashlight? Well, they walked over. Why did they walk over with a flashlight? Why didn't they stay there? Because they were an idiot. Okay, we can eliminate situations like this, right? Is it possible that you could have idiots? Yes. This is being recorded, so I will not say what I was about to. So we have another lemma. Always walk in pairs. That greatly prunes the analysis, because now we know we don't have to worry about just 1 person walking over. Everyone has to move in at least pairs. There's a great story that when Kepler was trying to understand the orbits of the planets, he was looking at Mars. And eventually he proved that, from the data, the shape that fits the orbit of Mars is an ellipse. But he didn't have the equation in the standard form of the ellipse. So he didn't recognize that what he had showed that Mars was moving in an elliptical orbit. It was an alternate formula for the ellipse. And so there are times when you may not recognize that you've done something. So in this riddle, we will assume that people are smart enough to realize that, hey, we're all on the other side of the bridge. That they will stop. Okay? So the goal is to see how to formally attack problems like this. So we have 1, 2, 5, 10. So what are the possible states we could move to? How many moves do we have? 4 choose 2. What's 4 choose 2? So there's 6 possible moves. Okay? So we could move to 1, 2, 5, 10 star. We could move to 1, 5, 2, 10 star. We could move to 1, 10, 2, 5 star. We could move to, 2, 5, 1, 10 star. We could move to 2, 10, 1, 5 star. And the one we actually care about, is this all in focus? Yes. We can move to, oh no, okay. Did I move 1 and 2 over together? No. So we could have 5, 10, 1, 2 star. 1, 2, 3, 4, 5. Okay, so there's the 6 possibilities. So if I start at this state, I can flow to these. And I can keep track of how much each costs. This costs 10. This costs 10. This costs 5. This costs 10. This costs 5. This costs 2. Now on the next step, what can I do? Right. So when we said you never send one person back, that was a lie. When do you never send one person back? We have to fix that statement. It's a little bit wrong.
Never send one person forward to the other side of the bridge.
We never send one person, always walk in pairs to the other side. And then do you always return singly? So do you always return singly? Or maybe for this problem you always return singly, but if I had more people, would I not want to return singly? Could it be advantageous? It's not as clear. We could do a little bit of analysis and a little bit of thinking. Do we want to have maybe multiple people come over? So maybe we have a bunch of fast people, and then eventually we send a huge number of fast people back. Well, they'll always go at the slower speed. That might be better than doing 2 trips. So maybe we could send multiple fast people back. It's not immediately clear. Maybe always walk in pairs to the other side, maybe on first move. As the problem becomes more and more complex, it's possible that this could fail. On the first move, we clearly want to send at least 2 people over. To send one person over on the first turn is stupid. It's a technical term. To send one person over on the last turn is also stupid. So we know the first and the last moves have to be just 1 turn. Anything else, it's still in flux. Okay? So you really want to be careful. It's easy to make extra assumptions and to try to look at what you're doing with too much of a focus on a special case. So now on this one, we've got 5, 10, and star. Do we want to send 2 people back? No. If we send 2 people back, we've just negated what we've done. So you either want to send 5 back or 10 back. So we can get to 1, 2, 5, 10 with the flashlight here, or we can get to the flashlight 1, 2, 10, and 5. Now the amount of time this takes, let's keep track. This would be, to set over here would be 10 minutes. No, it would be 5 minutes. And over here, this would be 10 minutes. So we know if we take this path, we would definitely be done. At this path, we're already at 15, and we've got the 5 here. So we would know we would not have to continue along this path. But it might be possible to reach 1, 2, 5, 10 in another way that's short enough. So we should keep this open, but we know that this path is not going to work. So again, I really find diagramming something like this a really good way to see what's going on. And then this is now a very formal procedure. Now I've got 1, 5, 2, 10. I could send 2 over, in which case I come to here. And that will be 2 minutes. So that's already that's already 12 minutes. I've got to do at least 2 trips. So this is really beginning to look like a bad node. Because I've got to send the 5 over. That will get me up to 17. And even if the 1 can get over immediately, somehow the flashlight is chucked, that's going to be 18 minutes. All right. So I could send 2 over. I could also send 10 over, get 1, 5, 10 with the flashlight and 2 over here. And if I do that, I've sent 10 back. How many configurations am I going to have in this second row? I've already got 3 over here. How many do you expect? You expect 4? Why 4 in total?
Well, it's just 3 with flashlight on the left and 1 person.
Yeah, there's 3 with the flashlight and 1 person on the other side. So you only have one more case to look at. I've got 1, 10, 2, 5. I could send 2 over and get 1, 2, 10. And that would take 2 minutes. So this path so far is only 7 minutes to here. What this tells us is there's no way we would do this path to get here. If we wanted to go through this place, this is a better way. We could also send 5 over, get 1, 5, 10, 2. And that would be 5 minutes. Now we've got 2, 5, 1, 10. We could send 1 over and get 1, 2, 5, 10. And if we send 1 over, that's going to be 1 minute. We could have 2, 5, 10, 1. I don't think we've written that one yet. 2, 5, 10, 1, and the flashlight here. And if we send 10 over, that's going to be another 10 minutes. We have 2, 10, 1, 5. We could send 1 over and get 1, 2, 10, 5. That would be this one over here. And that would be, we're sending 1 over. So that'd be 6 minutes. Oh, sorry, 1 minute, sorry, 1 minute, thank you. And then we could send 5 over and get 2, 5, 10, which is right over here. And that'd be 5 minutes. And then we have 5, 10, 1, 2. We can send 1 over and get 1, 5, 10, 2. And that's going to be 1 minute. Or we can get 2, 5, 10, 1. And that will be 1 minute, 2 minutes. Right. So here's my question. For these secondary arrows, do we want to record the additional time, or do we want to record the total time it takes? Well, it gets complicated because as we're over here, we have multiple paths, right? So the question is, we could just keep analyzing this with the computer, and we can keep adding more and more rows, more and more levels. The other thing is, we can start trimming as we go along. All that matters is, what's the shortest path to get here? Once we get here, it doesn't matter how we got here. So this is extremely important. There's no partial credit. There's no bonuses for having, say, certain people walk together. So in my probability class, I talk about an interesting problem. Imagine you have a group of 4 people, and you want to form a group of 2. And everybody is equally likely to be chosen. Okay? What's the probability 2 people are together? So you have 4 people, group of 2, all equally likely to be chosen, all people. What's the probability A and B are together? Well, if you form one group of 2, then the people who aren't chosen are another group of 2 if you want.
So we will see them. We'll see them as.
Yes, we'll see them as 2 groups of 2. So think of it as the Starbelly Sneetches from Dr. Seuss. So what's the probability that 2 people, A and B, are together? Either both chosen or both not chosen. If you've seen probability with me, you're not allowed to answer. So for this problem, I've got 4 people. I'm going to form a group of 2. What do you think the probability is? 1/6? Why 1/6?
Because there's 6 different groups you could make, and that's just choosing one of them.
So there's 6 different groups. It all comes down to how you read things. Okay? You can view the answer as 1/4 choose 2. Because there are 6 groups, and with 6 groups, you have a 1 in 6 chance.
But isn't in the case that
Right.
But CD is one of the 6 groups, right?
Mm-hmm.
So
So would it be then 1/3?
2 times that? I don't know. I'm just asking you.
So do we think it's now 1/3? So maybe is there a factor of 2 here? This is a hint. It's ABBA. Why is ABBA a hint? Anybody know the history of ABBA? They split up. There was more than a split up. They originally formed, then they got married in pairs of 2, then they got divorced in pairs of 2. And I believe they were offered $250 million to get back together, and they said, no, thank you. We're quite happy not to get back together. So when you are forming a group of 2, you will make damn sure you do not put somebody in with their ex. Each person will be equally likely to be chosen. But there are certain combinations that will never happen. So it really matters how you phrase things. So if you say each person is equally likely, that does not mean each subset of 2 is equally likely. And there's some other problems where that is the case. And we may do one of those on Wednesday, where it's very important how you read it. It's very easy to put in some additional assumptions. When you say each person, you're choosing uniformly among all the possible groups. No, I'm not choosing uniformly among all the possible groups. I could have this person hates this person. Or conversely, this person loves this person and would not want to be in a group with anybody but. So you have to be careful. For this particular problem, it doesn't really matter how you get to these places. It just matters that you get to them. So here, this is a path 10, 10. We can also get to this path with a 5, 2. So we would never have this path. This path is a 15. This path is a 12. So we know we would never want to go to 1, 2, 5, 10 on the first move. Anything that comes here, we have better ways coming out. So we can immediately eliminate this. All right, now for this one, we have 10 and 2, and we have 10 and 1. So we would know we would not do this 10, 2 path. Now, from here, to get from here to here, that's going to be 20. All right, we know 20 is right out. So what we're doing now is we're doing a lot of really good formal analysis. Okay. So essentially, we seem to be saying if you move 10 on the first turn and move 10 back, this is bad. Okay. Not that deep right now. All right, let's look over here. 5 and 5 is 10 to get here. But we can also do a 2 and a 1, which is much better. And then the other place where this can go is this can go to over here, which would be 7. Can we get here better than 7? No. So the other path here was 5 and 5. So this possibility is still alive, that maybe we send 2 and 5.
The other pass 1 and 5?
Let's see. Did I treat it wrong?
Yes, it's 1 and 5.
Oh, because we then sent 1. Oh, we sent 1 back. Oh, good. Oh, we were looking at the wrong number. Okay, we sent 1 and 5 back. So we've eliminated this one now. Good. So we saw the 2 different things it went to. They were faster ways. Okay, so now we can send 1 and 10 over and get here in 10 steps. Or we can do in 20 steps, or this one and get there in 10 steps. So we know we're not going to come down like this. And the other possibility is we could get here in 11 steps. That's still alive. Okay, now this one here, we can get here in 10 steps, or we can get here in 4 steps. Okay, we're not going to get there in 10 steps. So we can eliminate that. And now the other one is we can get here in 6 steps. I don't think we can beat that. So now we have 3 possible first moves and 3 possible second states. Or do we have 4 possible second states? We have 4 possible second states, sorry. 3 possible first moves 4 possible second states. And what we can do is we can keep the running time. So over here, this is taking us 4 units of time. This is taking us 6. This one, this one was 3. Oh yeah, this one was 3, thank you. Was this the one that was 6? This one was 6. And this one was 11? Okay. At this point, you would probably want to rewrite the graph. Given that all the stuff that worked was all the way over here, and we've got all the arrows coming across like this very messily, you would probably want to rewrite this. But in terms of formally going through this and analyzing this and proving that this is the best, proving that there's not a better way of doing this, this is to me the most methodical way I know, is to turn this into a graph problem. And then spend the time pruning each layer. We know we can do at least 19 minutes. So as soon as we have something that was going to take more than 19 minutes, so over here, we're at 11. That's still in play. Well, but let's think. The best we could do is send, this is where we start doing some analysis, is send 5 and 2 over is 5 more minutes. Send 2 back, send 1 and 2 over, or we could send 1 and 5 over. So it's how much work do you really want to do. The computer can start enumerating all the cases. And in fact, what you could do is you could look at a flow chart where you start off with 1, 2, 5, 10, flashlight, nothing, and end with nothing, 1, 2, 5, 10, flashlight. So I think this is enough to give you a sense of how you would finish this. The analysis isn't too bad. It's now small enough that you can break into little cases. Okay. Well, happy with this? Okay. So the next one is either the legal 21 problem or the egg drop problem. Any preferences? I'm also happy to state what they are. So the legal 21 is you have the numbers 1, 5, 6, 7. And you can combine them using any binary operations you want, plus, times, minus, divide. You can use all pluses, all divides, whatever you want to do, and you must get 21. You can't combine 1 and 5 and make 15. The other one is you have 2 eggs, and you have a building that's, say, 100 floors. And you can keep dropping an egg until it shatters. If the egg falls safely, you can drop it again. And you want to figure out what is the highest floor you can safely drop the egg from. Did we do legal 21? Okay, was that on the midterm? Okay. Okay, then if we did legal 21, then let's do the egg problem. Can somebody give me a strategy? So once crack, it's gone. Else can we use? So what do you think I want to ask for today? Yeah, determine the minimum number of times. But be more specific by minimum number of times. Be more specific. There's got to be some other assumptions going on. So one of the hardest things in a lot of these problems is you may be assuming things that you don't realize. And so they do this to you all the time in competitions. I want to make sure that people in Swarthmore are able to see this, so I'll try to draw it pretty big. All right, I've got a 3x3 set of dots. How many of you have seen this problem? Okay, I see at least one person knows where I'm going. So it's amazing you just lost your voice. It'll come back soon. You want to draw 3 straight lines going through these dots, but you can't take your chalk or pencil off the paper. Can anybody see a way to do it with 5 straight lines? Yeah. 1, 2, 3, 4, 5. I can do it with 5 straight lines. Can anybody see a way to do it with 4 straight lines?
So is the question here not to use your
Well, right, there's probably an assumption going on in the background. So for this one, is it possible to do with 4 straight lines? Can you see where to do with 4 straight? Okay, how would you do with 4 straight lines?
Basically, 1, 2.
So let's see. 1, 2, 3, 4. Okay, that should work. So I go 1 and I get those 3. 2, I get those 3. 3, I get those 3. Those and those. So something like that. So 4 is not so bad. How about 3? Doesn't seem possible to do this with just 3. What's the maximum number of dots you can get on a line? 3. And so it's theoretically, okay, it should be, it's at least possible to do with 3 lines because each line will give me 3. But I'm going to have to then pivot and I'll have the same point again. So it seems like I'm going to be double counting a point. And so the solution is that you are subtly assuming something. What are you assuming about the points on this problem? When you hear point, what do you think of? You've got to think of something, you're math majors. When you hear point, what do you think of when you hear the word point? Give me the definition of a point.
Fixed coordinate in some space.
Okay. And so coordinate, that's an exact measurement of length, I'm sorry, of maybe x, y, z in 3 dimensions, or x and y in 2 dimensions, or x in 1 dimensions. Does it have length? Does a point have length? Width? Height? Do these have length, width, and height? You know, I said, oh, I'm drawing these large for the people at Swarthmore so that they can see it on the video. I did not draw points that are dimensionless. I drew physical points. The solution for this riddle is you come up here through an angle. And you get, I'm probably not drawing this perfectly because of, but that's how you get through all of them. Is what this is subtly having you assume is that these are pointless objects. And that these are dimensionless objects, that there is no length, there's no width. But if there is length and width, we have the possibility to pass through these points at an angle. When you are looking at a problem like this, there's always assumptions that you're making. And the point is you don't realize what assumptions you're making. This is why I'm willing to spend so much time on these riddles. It is extremely unlikely that later in your life you will be dropping eggs from buildings. You may want to, but you probably won't. What you will be doing is you will be in situations where people will be assuming things around you. The financial crash from around 2008, a lot of it was caused by people applying a math formula to places they had no justification doing so. They just assumed, oh yeah, the conditions are fine. No, you check the conditions and you see, ooh, they're dependent. This formula assumes things are independent. Does it really matter that they're independent or dependent? Let's take a look. That would have been really good to do. When you're dropping this off and you're trying to find the minimal number of drops needed, what are you assuming? So there's so many assumptions, so little time.
Can you drop the egg at any height?
So we'll assume we can drop the egg at any floor, at any of the 100 floors. So we will assume we can drop the egg at any floor. But we are assuming something. I'm giving you that. That there is a floor at which the egg will crack.
Are we assuming that we don't want the egg to crack?
Well, we want to find, it seems reasonable that we want to find the floor at which the egg will crack from in the fewest possible drops.
To the lowest floor that they will crack from?
The lowest floor that they will crack from.
Maybe we're assuming that there are some floors at which it won't crack.
So I'm willing to tell you that it will crack from the floor. How many of you know the birthday paradox? How many people you need in a room to have at least a 50% chance that two people have the same birthday? So it turns out the answer is much smaller than you might expect. It's only around 21, 22. When you are doing the birthday problem, when you are assuming, when you're trying to figure out what's the probability that two people share a birthday, what are you assuming about people in the room? I'm sorry? No twins. My wife's an identical twin. This is a really easy game to play at reunions on her side. It's not that challenging. We also assume that nobody was born on February 29th. So I'm assuming here, I'm not actually assuming, I've actually told admissions, I don't want any math majors who were born on February 29th because it just screws me up when I have to do problems like this. And so they're welcome to come to Williams, they just can't take my classes. And if you look very closely, we are an open campus, but there is nothing that says as a professor I cannot discriminate based on day of birth. Because that could affect everybody equally likely. I am allowed to say, and I'm saying this to the camera right now, if you're born on February 29th, I do not want you in any of my analysis classes. Algebraic class is fine, but not analysis. Because I want to be able to talk about the birthday problem. So we are assuming that all birthdays are equally likely, and each person's birthday is chosen independently from all others. When I'm trying to find the floor, what are you assuming right now? The eggs are equally likely to break. Be a little bit more specific. From each floor. That I'm choosing the floor at which the egg will break uniformly. What if I didn't choose the floor that the eggs would break from uniformly? What if there was a bias in how I choose? Would that affect how you drop the eggs? It should. Let's say you know I don't want eggs to break from a floor lower than 90. Would you waste time dropping eggs from 30 or 40 or 50? So we want to assume the key floor is uniformly chosen at random. Okay? If we don't put that in, then that could affect your strategy. So let's assume that the number is equally likely to be anyone from 1 to 100. Now what strategy do you want to use? If I don't have that assumption, then if I'm going to be choosing high floors, you may not want to spend too much time on the smaller ones. Can somebody give me a really bad strategy that will find the floor? Start at 1. Go 2, go 3, go 4. So that one will work. And in fact, that will work with just one egg. And if you only have one egg, is there a better strategy? No. Because as soon as the egg cracks, if it didn't crack on that right floor. So if you only have one egg, that's the best strategy. So again, this goes back to something we've always talked about. Whenever I give you a problem, look at a simpler related problem. This is the problem with 2 eggs. What would be the problem with 1 egg? What do you think comes next? The problem with 3 eggs, right? So think about this for Wednesday. Think about how you would drop the eggs. And try to figure out where you want to put it. There's a lot of good stuff about choosing things randomly. There was a mistake years ago with the green card lottery for the US. They chose the people randomly, but only from people who were born in the first few days of a month. And so it was a random draw, but it was not a random draw from all candidates. But there was no discrimination based on whose birthday it was where. And there was actually a legal challenge to the US green card draw. I will try to find that information. Okay, this is a good place to stop.